Assalamu alaikum. Thank you, dear chairman and dear professor, dear assistant. I'm very happy to present for you our work on student prediction of failure pressure of pipeline corroded for a hydrogen application with linear and non-linear regression method. The content of our presentation is, first of all, I will present the background of a corroded pipeline failure. After that, the empirical models used to predict the failure of pressure. And after that, I will present the regression method, linear and non-linear, with the finite element model implemented in this work. After that, I will present the result and our interpretation, and I will finish this presentation with the conclusion. For the corrosion, is the most important problem with steel pipe due the method used to predict the failure of pressure. We have the empirical method like ASME B31 modified and DNV method, and also we have we can use the finite element model to predict the failure of pressure. In this work, we aim to predict the failure pressure by employing experimental data and the regression techniques, especially linear and non-linear regression method. This research aims also to establish a more accurate and reliable analytical model for predicting pipeline failure pressure. To achieve this objective, our objective, we adopt this approach. So we have a pipeline with a single defect, inner or outer single defect. We can begin this analysis with experimental analysis results, and we implement another model, a finite element model, and we use also empirical model. After that, we use the regression method like regression linear and non-linear, and we can also use an artificial techniques or algorithm to predict the pressure of failure. After that, we can use all of this method to predict the failure pressure in the case of a single defect, outer or inner defect. For the shape of defect, we have many kind to adopt this defect or corrosion defect. We have the rectangle approach and the parabolic approach. We have also a mixed approach and the actual according area. In this work, we adapt to use a rectangle shape of defect, and for the empirical models, we adapt to use the ASME B31 modified and the DNV LPF101 to predict empirical failure pressure. For the numerical model, we adapt to use the Bomis's criterion to evaluate the reliability of this kind of pipeline. For the materials of pipeline, the empirical, the result experimental data is with three kind of steel: X52, X65, and X80. For the numerical model, we use this half part of pipeline due to the symmetry of structure. We apply inner pressure, and we apply this boundary condition in the other side. After the simulation, we can predict the maximum of Bomis's stress in the corrosion zone of this pipe. With this numerical model, we can evaluate the influence of the depth of a single defect, and we can calculate the equivalent stress of vomices. After this model, we move to use regression models. We adapt to use experimental data. With this regression model, we adapt to evaluate the R squared is equal to SSR divided by SST, with SSR is the sum square of square regression, and the SST is the total sum of squares, and the R squared is the criteria to evaluate the error of our regression model. For the first model, is a linear regression model. We can adapt to use this to propose this analytical model with D is the inner diameter of intact pipe, and T is the thickness of intact pipe. D is the depth of the corrosion defect, and L is the length of corrosion defect. For sigma u is represent the ultimate stress of these materials. And for the non-linear model, we can use many kind of analytical non-linear models, like exponential model or logarithmic model. After the analysis of the data with the linear regression method, we can remark after this analysis R squared equal to 90-30%, and we after the fitting of this data we take this equation, analytic equation, to predict the failure pressure of this kind of problems. This figure represents a comparison between the experimental data and the result of the regression linear regression model, and we can remark a good agreement between the two approaches. And for this, in this case, or this figure represents a comparison between experiment data and the analytical data and the regression linear regression method. For the analytical result here, we use the ASME B31 as a function to calculate or estimate the failure of pressure. And for the second regression, non-linear regression method, we can we can calculate the R squared of this model, and we remark after the analysis R squared equal 97%, and the figure represents a comparison between the experimental data and the non-linear regression model. And this figure represents a comparison between four models, experimental data and analytical model, and regression linear and no linear method. Finally, I will conclude with this conclusion. The present work uses two regression model, linear and no linear model, to predict the value of the pressure or the burst pressure of pipeline with a single defect or another single defect. After discussing the results, we can conclude these two models can use it to predict the failure of pressure. and we can remark the regression with the linear method gives R squared equal 33%, and with the non-linear method R squared equal 97%. It's clear the non-linear method is the best model of these two, as is evident. And the smallest, we can also with this model analyze the impact or the sensitivity of each parameter of our model or problems. The smallest impact on failure pressure is the length of the corrosion defect. Finally, the previous work we aims to use machine learning to predict the failure pressure of the pipeline corridor. And thank you for your attention.
Thank you very much for respecting the time allowed for your presentation. Just maybe the last slide. You mean not the previous. You mean the next or the future.
Yes.
The previous means
past.
Okay. Thank you. So
Thank you.
let's see with the audience, maybe maximum a couple of questions if someone has any question, please.
So
Thank you
for your clear presentation. My question is regarding the data used in this approach. Is the data used for the external corrosion? You use the pit gauge for measuring the well thickness or?
No, this data is literature data. Yes, yes. Because we have a problem with the hydrostatic experimental analysis with the inner or outer defect. For this, we get the data for literature work, and we work with this data.
For this data, it's recorded on ultrasonic testing or?
No, it's hydrostatic test. Éclatement. Test d'éclatement.
But for this result, for this data, we do measurement of dimensioning of the corrosion.
Sometimes we use comment dirais-je? En français, le défaut il est créé. On va créer le défaut et on fait les essais.
Le défaut intérieur, on utilise le contrôle ultrasonique pour faire le dimensionnement.
Et si l'analyse, lorsqu'on a une longue raison, généralement on utilise un robot pour scanner l'état de la structure.
Ça s'appelle le mais dans notre technologie, il y a de long range testing, utilisé souvent pour les pipelines enterrés. On peut déduire les sommes de niveau de corrosion. Merci.
Thank you for your remark.
Maybe another question.
Thank you.
Professor.
Okay. You can stay in this slide, please. You can stay in this slide, please. The last one. Conclusion. 20.
The last one.
Okay. So you write here prediction of failure pressure requires the use of the two regression models. So if you have the possibility to have the non-linear model, why use the non-linear model? Since the coefficient of correlation here, so the difference it's very big.
Yes.
So when we have the possibility to have non-linear models, so we can disguise the linear model.
Yes,
so this is my question. No need to write here requires it's mandatory, obligatory. Okay. So this is just a remark. Thank you for your presentation.
So now maybe if there is no question, we have a break. I think everyone now overwhelmed. There is maybe last presentation, sorry. Yeah, so I'm sorry for people are already thinking about the bench. So we have another presentation.